Launch right into that. I want to talk about the bell ringer. So your bell ringer, I think, was quite simple. You had something like 2 to the 5, asked you what is the base and what's the exponent. Well, 2 is the base, and 5 is the exponent. But then you had something that looked a little different, 2 to the x. And 2 to the x, in this case, the base is still 2, but the exponent was x. So this is a little bit different. We're not used to seeing a variable in the exponent. We're used to seeing a variable as the base, like x squared. That would be a quadratic function. But when a variable is the exponent, we have what's called an exponential function. That's where it gets its name from, because the variable is in the exponent. So let's explore what an exponential function is and what it looks like. So if I were to give you f of x equals 2 to the x, and I were to ask you to graph this, what would be a good first step? If I was going to graph, what would I do? What's the first thing? I would create a t-chart, right? A little table. Okay. So that's what I'll do. X, f of x, -2, -1, 0, 1, 2. So I've created my t-chart, and all I have to do is the same thing I always do, which is just plug it in. I'll start with the easiest one, which is 1. 2 to the 1, what's anything to the first power? It's just itself. 2 to the 1 is 2. Then plugging in 2 for x, I get 2 squared is 4. Then I'm plugging in 0 for x. 2 to the 0, what's anything to the 0? 1. So that's 1. And then 2, plugging in -1, 2 to the -1. What do I do when I have a negative exponent? I take something from the top, I flip it. Yeah. So it goes, instead of 2 to the -1, it becomes 1 over 2 to the 1, or just 1 over 2, 1/2. And then if I'm plugging in -2 here, if I'm plugging in -2, that becomes 1 over 2 squared, or 1 over 4. And I've completed my table. Okay. Once I've completed my table, I can go ahead and graph my function. And so that's exactly what I'm going to do. I start off by creating my coordinate plane here. One, 2, 3. 1, 2, 3. 3, 4, 6, 7, 8. And I'm actually going to extend this out to 3, and I would get 2 to the 3, which is 8. Okay? And once I have that, I go ahead and plot my points. Start with the easy ones. 0, 1, then 1, 2, then 2, 4, then 3, 8, which is up here. And then -1 is 1/2, which is here. And -2 is 1/4, which is here. And now already from my points, I can see the general shape of an exponential function. But I want to explore this a little bit further. What if I made x even smaller? For instance, if I made it, instead of just -2, what if I made it -10? Well, this would be 2 to the negative 10, or 1 over 2 to the 10th. 2 to the 10th is a really big number, so 1 over that is a really small number. And what if it was negative 100? It would be 1 over 2 to the 100, right, which would be even smaller. And so it would get smaller and smaller and smaller the more I go in the negative axis. Getting closer and closer to what? 0. Good job. It gets closer and closer to 0, but it never touches. Okay? And so I can graph the general shape of my function here. And I said it gets closer and closer to 0 and never touches. There's a word for that. It begins with an A. Yes, good. Asymptote. A-S-Y-M-P-T-O-T-E. Got to remember the P in there. Asymptote. So it gets closer and closer to the x-axis and never touches. This is an exponential function. This is the graph of an exponential function. This is what the graph of an exponential function looks like. Now there are a couple of characteristics about this exponential function that I want to point out to you. The first characteristic we already spoke about is this asymptotic behavior, where it gets closer and closer to the x-axis, closer and closer to 0, but never touches. Okay? The second aspect I want to show you is the general shape, and what it does on the right-hand side here. It grows, and it grows at a faster and faster rate. Okay? And this is an exponential function, and it's growing exponentially. Now, some of you guys might have heard people talk in everyday language, oh, something is growing exponentially, like the amount of people walking on the roof is growing exponentially, or like the amount of pigeons in New York City is growing exponentially, or the amount of peanuts in Africa is growing, I don't know. But the point is that you've heard, have any of you guys heard people say, oh, it's growing exponentially, right? Yeah, it's kind of like a phrase of speech that a lot of people say. The reason why is because exponential functions, exponential growth is faster and faster and faster. You see, it kind of starts slow, but then it goes, right? Okay, but it's not just a thing that you say, oh, it means it's going fast. It's actually a very specific thing. If something is exponentially growing with exponential growth, it means it's following an exponential function. And so the question is, what is that? What's actually happening? Well, let's take a look. Let's explore this further. What if I went out a little bit further? Instead of just from 3, I did to 4. Well, it would be 2 to the 4th, which would be 16. And if x was 5, it would be 2 to the 5th, which is 32. If it was 6, it would be 2 to the 6th, would be 64. If it was 7, it would be 128. 8, it would be 256. 9, it would be 512. And 10, it would be 1024. And notice it's growing at a faster and faster rate. At 10, it's already 1024, right? What's it doing every time? Doubling. That's characteristic of an exponential function. You're not just going up linearly. A linear function just goes up linearly. It goes up by 3 every time. 3, 3, 3, right? A quadratic function goes up by the square of a number, right? So if I have x squared, it grows by the square. So 1 squared would be 1, okay? 2 squared would be 4, oh, that matches. 3 squared would be 9, that's actually higher than this one. 4 squared would be 16, 5 squared would be 25, 6 squared would be 36, and then you see that the exponential function starts taking off, right? 7 squared would only be 49, but the exponential function is already at 128. 8 squared would be 64, 9 squared, 10 squared would only be 100, but the exponential function is at 1,000, you see? So when people say growing exponentially, if it's a mathematician that's saying, they're probably talking about an actual exponential function. But the reason why people say it is because exponential growth is this very rapid growth. Does that make sense? And it's like doubling or something every time. Now, there are 2 good examples of exponential growth from real life. This isn't just like a random math thing. The first example that I'll give is like bunnies. Bunnies are known for their like massively quick reproduction. Like you get 2 bunnies together, they'll make 8 bunnies really fast. But then here's the thing: you have 8 bunnies now. You have 4 pairs of 4. Okay, those 8 bunnies then make like 64 bunnies, and then those 64 make like 512 bunnies, and then those 512. So it grows exponentially, multiplied by 8. Now, obviously, it's limited by wolves and food supply and things like that. But if you leave bunnies alone in bunny paradise, they will make exponentially growth bunnies. You understand what I'm saying? Now, the second thing is something that's a little bit more relatable, though a little bit less humorous, is mitosis or meiosis. I don't remember which one it is, or maybe it's both. But the splitting of cells, right? You guys know about this? If mitosis, thank you. If one cell splits, it makes 2 cells, right? And then those 2 cells then make 4. Those 4 then split to make 8, and then make 16, then 32. Oh, you see this? In our human body, in everything, basically, mitosis, the splitting of cells is growing exponentially. That's why babies go from this to like really fast, because their cells are growing exponentially. The point is that's true. It actually does happen, okay? This is a real thing, and it's called exponential growth. You see? Is that clear? Okay, so that's an exponential function, exponential growth. All right, so let's take a look. 2 to the x, that's what I just graphed. That's that right there. Okay. Notice the asymptote here. No matter how far I zoom out, it never crosses this x-axis. You see? And I keep zooming out, and the growth is really fast. You see that? The more I zoom out, the faster it looks like it's growing. Okay. Now, what if I did 5 to the x? Do you think it would grow faster or slower? Faster. Yep, 5 to the x. And then if I did 10 to the x, it grows even faster, you see? Okay. What about if I did 1 to the x? If I did 1 to the x, it's a straight line. But why? Why would it be a straight line? Well, let's explore this. If I gave you f of x equals 1 to the x, and then said, create my x f of x table, -2, -1, 0, 1, 2. Well, what's 1 to the second power, 1 squared? 1. What's 1 to the first power? 1. What's 1 to the 0th? 1, -1, 1, 1. No matter what, it's always 1, you see? So 1 to the x isn't really an exponential function, it's just 1, okay? But more interestingly, what about if I have 1/2 to the x? Okay. Well, when I have 2 to the x, I'm doubling every time, right? Like the cells splitting, I'm doubling every time. Well, if I have 1/2 to the x, I'm not doubling every time, I'm dividing by 2 or halving every time, right? So I'm cutting it in half every time. So instead of exponential growth, we get what's called exponential decay. And we see that it's basically the same. It looks very similar. The shape of the function is the exact same. It's just flipped across the y-axis here, you see? So here's exponential growth, here's exponential decay. And exponential decay is also interesting and can be found in our real world. Notice we still have this asymptotic behavior right here where it's never touching the x-axis. And it's falling from here. It's falling really fast, but then it's falling at a slower and slower and slower and slower rate. That's characteristic of exponential decay. So it falls really fast in the beginning, but then it takes a long time for it to get, it decreases at a smaller and smaller rate. What's an example of this? Did you guys hear what happened in Fukushima like 7 years ago? A power plant, nuclear power plant in Japan? No? So, yes. You did. It didn't get bombed, but there was a tsunami. There was a tsunami that hit it, and it leaked radioactive water into the Pacific Ocean, right? And so a lot of people were freaking out about that and were pretty scared. And the reason why is because, first off, radioactive material is harmful to life, though God has created a wonderful, wonderful world in that we are able to process radioactivity. Vegetables, animals, we're all able to process it even though it can be deadly. But with that said, the thing that's scary about it is that not only is it hazardous to human life, but it takes a really, really long time for it to go away. It's not just like a chemical spill, which like over 10 years is just gone. No, radioactive material decays over a very long period of time. And it decays in a very specific way. It decays in an exponential pattern, exponential decay. What does this mean? Have you guys ever heard of a half-life of radioactive material? Half-life? Heard about it? How does half-life work? Well, let's say you take like plutonium or something. Well, how it decays is it cuts in half over a certain half-life. So let's say the half-life is 60 years. You guys with me? Some of you guys? Okay, look. So say the half-life of plutonium is 60 years, all right? Well, what that means is that say you start with 1,000 pounds. Okay, you've got this plutonium shooting off gamma particles or something. Well, in the first 60 years, it goes from 1,000 pounds to 500 pounds. Okay, it cuts in half. But then in the next 60 years, that it doesn't lose another 500 pounds, it just cuts in half again. You see? So it goes from 500 to 250. And then 60 years later, it goes from 250 to 125. 60 years later, it goes from 125 to 62.5, and so on and so forth. So even though you lost 500 pounds in that first 60 years, to get down to a small amount takes a long time. Well, that's exactly what we see here with exponential decay. Okay, so this is real world type stuff, and if I show you a graph of the half-life of uranium. First off, the half-life of uranium is 4.5 billion years. Okay, so I don't think there was uranium in that power plant, but anyway. So there you go. There's the half-life, a graph of the half-life of uranium, and we see that over time it decays in this exponential decay pattern. See that? That's pretty cool. Okay, so that's an example of exponential growth and exponential decay. Are we clear on that? We feel like we kind of understand exponential functions and a little bit about how they show up in nature? All right. Now, I hope you guys are excited. See, this stuff excites me. You guys, we should you guys can talk about uranium stuff. No. Anyway, so I have this graph here that I made on Desmos. And this has the general form. So if we're going to talk about exponential functions, we better talk about the general form. The general form of exponential functions is a times b to the x. What are a and b? They are constants. Okay. So a times b to the x. And an example of this could be like 3 times 2 to the x, or negative 2 times 4 to the x, or 5 times 1/2 to the x. You see? And you don't have to necessarily write those down, but that's just an example of the general form. Now let's take a look. I have these sliders here that change a and b. Well, the first thing to recognize is that a is the y-intercept. If right now the y-intercept is at 1, a is 1. If I make a equal to 2, my y-intercept goes up. See, as I change a, I change my y-intercept. A is 5, my y-intercept is 5. See? If I make it go down, what do you think is going to happen if I make a negative? What do you think will happen? If I keep going down, it's going to flip. Yeah, you see? It's going to flip the graph. So a is negative 2, there's my y-intercept at negative 2. So the first take home here is a is the y-intercept. And that's always the case as long as the function is written in this form. Now, I'm going to make a equal to 1 again. Now b, we remember, if b is equal to 2, that's what the graph I started out with, which is 2 to the x. If I make it higher, it stretches it out more. If I make it lower, first off, if I get to 1, then we see that I end up with this graph here, just a straight line. But if I make it less than 1, like for instance 1/2, then look what happens. It goes to radioactive, or not radioactive, exponential decay. So if it's more than 1, it's exponential growth. You see, exponential growth, until I hit 1, and then less than 1, it's exponential decay. So you see, exponential decay, exponential growth. Decay, growth. Clear? So when b is between 0 and 1, it's exponential decay. When b is greater than 1, it's exponential growth. And that's the second takeaway. So when b is between 0 and 1, I have exponential decay. And when b is greater than 1, I have exponential growth. Bye-bye, Jenna.
Bye.
Have a nice day. Okay. So if b is between 0 and 1, it's exponential decay. If b is greater than 1, I have exponential growth. For the record, guys, this exponential thing that I'm talking about is so far-reaching. It is so far-reaching that it's I can't even begin to describe to you what exponential functions model. Just really quickly, if I have a tree stump, right? And then sorry, I shouldn't have said it. I gave it away. If I have a straight line, and then I split it off at about here and create 2 branches, or 3 branches right at the end there. And then I create 3 branches at the end here, and 3 branches at the end here. And then I keep going. And I split them off into 3 and 3, and then keep going and keep splitting them off, right? What does that look like? Looks like a tree, right? Well, that's how a tree grows, okay? A tree grows with this exponential pattern. It's one trunk, and then 2 or maybe 3 smaller branches, big thick branches, then 3 off of each one of those, and then 3 little ones, and then finally it is leaves. You see? There's these patterns that show up in the world, and it's not just random, it's mathematical. So exponential decay is when b is between 0 and 1. So it's exponential decay. And exponential growth is when it's greater than 1. Which leads to a fundamental question. What if b is less than 0? What if b is negative? What if b is negative? Well, let me show you what happens here if I make b negative. If I make b negative, my function disappears. Why does it disappear? Why can't b be negative? Well, let's say it was negative. Let's say I had f of x equals -2 to the x, so b is -2. And let's say I then ask you for f of 1/2. Well, that would be -2 to the 1/2 power. But what's another way of writing something to the 1/2 power? Square root. Good. Square root of -2. But is square root of a negative number a real number? No. So this is why b can't be negative, because you end up with situations where you're taking roots of negative numbers. Okay? Is that clear? Okay. You guys are very quiet today. Mercy. Okay. All right. Last thing. End behavior. As x goes to -infinity, what does the function do? As x goes to +infinity, what does the function do? Okay, in this case, as x goes to -infinity, that means I'm going to the left. What's my function doing? Going up, which means the function is getting closer to, it's going to infinity. Good. And as x is going to the right, my function is getting closer and closer to what? 0. Good. So that's the end behavior of that one. And then here with exponential growth, as x goes to negative infinity, as I'm going to the left, my function is getting closer to 0, right?
0.
Yeah, as I'm going to the left, my function is getting closer to 0. And as I'm going to the right, my function is getting closer to infinity. Does that make sense, guys? Okay. All right. So that's the lesson. So what did we learn? We learned about exponential functions. We learned about the form of exponential functions. We learned about exponential growth, exponential decay. We learned how to find the y-intercept. And we learned about end behavior. Okay? All right. Now, homework. What's your homework? We also learned how to graph exponential functions, clearly. What's your homework? Homework is page 453. Numbers 1 through 14. Now, I'm going to do a couple with you. Who can tell me what the last two words are of this sentence? Graph calculator. Raise your hand if you have a graph calculator.
Is that like the Texas one?
So you're not going to be required to graph using the graphing calculator of these ones. On 9 through 14, you will be required to graph because there's a coordinate plane you're supposed to graph it. But on these ones, you're just getting A, B, and the y-intercept, which is actually really, really simple. So let's go through a couple of them to start. So 1 through 8 you're not graphing. So let's do number 1. Number 1, remember the form of my function is f of x equals a times b to the x. Well, that makes this very simple. A is equal to 2. B is right there, is equal to 3. But what's the y-intercept? What did we say the y-intercept always was? A. A. Y-intercept is the same thing as A in this case. A is the y-intercept. So the y-intercept is at 2. Okay? That's it. That's the whole problem. So go ahead and do number 3 now, and then I'll go over it. You will for 9 through 14, but not for numbers 1 through 8. All right, so this is pretty simple. What's A, class? Negative 5, good. What's B? 0.5. And since A is negative 0.5, what's the y-intercept? Is negative 5. Good. All right, you guys understand that? Okay. Now the next two, now down here, numbers 9 through 14, you are going to have to graph because it provides you with the coordinate plane. So here we go. Sorry. All right. So when I'm graphing, what's my first step?
Table?
Yes. hate the table. X, f of x. -2, -1, 0, 1, 2. Those numbers are generally good for your exponential functions, no matter what you're working with. Then I just go ahead and plug in. I'll start with 1, 3 times 3 to the 1. 3 to the 1 is just 3, so this is 3 times 3 is 9. Then 2, 3 times 3 to the second power. Well, 3 squared is 9, so it's 3 times 9 is 27. Next, I have 3 times 3 to the 0th power. Well, that's 3 times 1, which is just 3. Then 3 times 3 to the -1, which is equal to 3 times 1 over 3 to the 1, which is just 3. Or 3 times 1/3 is just same as 3 over 3, which is 1. Next, 3 times 3. Good? Question?
Sorry, yeah, question.
Yeah.
You can only do the fraction or put the 1 over just one in the base, not both.
Yeah, because, question, if I'm multiplying and I have the exponent, do I multiply first or raise to an exponent first? Raise your hand if I do the exponent first. Okay, raise your hand if I multiply first. Okay, so PEMDAS, remember, exponent first, then multiply. And so that kind of, in a sense, answers your question. This 3 is by itself. I handle the exponent first, and then I multiply. Good. So 3 times 3 to the -2 equals 3 times 1 over 3 squared, or 3 times 1 over 9, or 3 over 9, which is 1/3. Then I go ahead and plot my points. Start with easy ones. 0, 3 is here. Got to be careful. Each of these ticks is 5. So 1, 9 is here. 2, 27 is here. Then -1, 1 is here. And -2, 1/3 is here. I'm going to go ahead and do my best. And after I'm done graphing, I have to make sure that I put my asymptote. Okay, what are my expectations for your graphs? Number 1, you have the asymptote here on the x-axis, so just make sure you can see the dashes. Number 2, the y-intercept is right here. It's A is always the y-intercept, so I want to see that point for sure. But definitely I want to see other points as well. At least a couple more. And then the most important thing for sure is the shape. I want to see that you know that this isn't just going off in a straight line, that it's got this curve and it's curving up exponentially. Any questions on how I did that? Yes, ma'am.
The asymptote is 3 for that?
No, the asymptote is always at 0. Whenever it's in this form, whenever it's in this form, a b to the x, the asymptote is always at 0. Any other questions? Okay. All right, last one, and then you can do your homework. Number 11. Number 11, you would have to use a calculator for. Okay. All right. So, what do I start with? Table. Gotta start with the table. You know, it's like Thanksgiving. Just put it all on the table. All right. -2, -1, 0, 1, 2. go ahead and plug in. In this case, the easiest one is 0, because negative 6 times 0.7 to the 0th power. Well, anything to the 0th power is just 1, so that gets rid of the decimal. This is just negative 6 times 1 is negative 6. Then I go to 1, negative 6 times 0.7 to the 1st power. Equals negative 6 times 0.7, which is negative 4.2. Hey, thank you. Negative 4.2, and then here negative 6 times 0.7 to the 2nd power equals negative 6 times 0.49, which is negative 2.94. Almost there, guys. Negative 6 times 0.7 to the negative 1 is equal to negative 6 times 1 over 0.7, or negative 6 over 0.7, which equals negative 8.6. And last one, negative 6 times 0.7 to the negative 2, which equals negative 6 over 0.7 squared, which just really quickly is negative 12.25, or negative 12.2. Okay, so I think that's pretty clear. The biggest mistake I see in this, guys, is people not knowing how to plug into the exponent. Okay, so the biggest mistake is just like plugging in for like just doing something almost silly, you know. Just there's your exponent, exponential functions. It looks weird when you're plugging in for the exponent. Okay. Then I go ahead and plot my points. Start with the easy ones: 0, negative 6, 1, negative 4.2, 2, negative 2.94. Negative 1 is negative 8.6. It's here. And negative 2 is negative 12, which is off the chart, but it's like here, basically. Somebody get that? Thank you. Thank you, Victoria.
Yes, she's.
Is this? Good.
Yes.
Okay. All right. So that's the graph. One last thing is I got to put the asymptote, and the asymptote's always at the same place when the function's in this form. Bye, Amanda.
Bye.
Have a happy day. See ya. Okay. That's it. That's graphing. That's graphing exponential functions. You guys can put it in the tool belt. All right. Your homework is page 453. Page 453. Numbers 1 through 14, with the caveat that numbers 1 through 8 is no graphing. So you don't have to graph for numbers 1 through 8. Any questions about this? Okay. All right. Good job. That's it.